This is Premise Podcast number 52, and today we're finishing off wind turbine blade design. This is part 2. If you want to get to listen to part 1, the link is right here. So let's continue. Last time we finished off with aerodynamic, right here, this aerodynamic section, and we're going to go on to blade twist and a whole bunch of other things. So just recapping, the blades on a wind turbine, they need to be obviously well designed to maximize the amount of energy that you produce from any given wind that you have, any given gust. And there are many different types of wind tunnels. And in podcast on 51, we go through a bunch of different ones. The first half of this bigger podcast series, I guess. And one way to maximize the amount of energy you get out of wind is the angle of twist. So like aircraft, for example, like airplanes, the twist of the blade on a wind turbine is not constant. So, and they discuss here, they say the lift generated by an airfoil section is a function of the angle of attack to the incoming flow. The inflow angle of the airstream is dependent on the rotational speed and wind speed velocity at a specified radius. So what that means is near the blade root, where it connects to the nacelle and all that, the blade is not rotating as quickly, the rotational speed is not as high. So the effective velocity that the blade is seeing on the air is different to when you go out to the tip, because the tip is rotating much faster, the rotational speed is much faster. So the angle that will produce the most amount of lift at near the root is not going to be the same as near the tip, because the angle that the velocity of the air is coming in, because it's moving faster near the tip, the blade, is different. So they say the angle of twist required is dependent upon the tip speed ratio and the desired airfoil angle of attack. Generally, the airfoil section at the hub is angled into the wind due to high rotation of wind speed to the blade radial velocity. So what that means is, because the blade is not rotating very quickly near the root, you can pitch it at a very high angle of attack, relatively speaking, and you'll be fine. Alternatively, in contrast, the blade tip is likely to be almost normal to the wind, and that's because it's rotating so quickly. You don't need it to be angled to the wind as you would typically expect, because the actual velocity that the blade is seeing at this point is very different. So they say the total angle of twist in a blade may be reduced to simplify the blade shape to cut manufacturing costs, but this may force airfoils to operate at a less than optimal angle of attack, where lift to drag ratio is reduced. So simplifications, while they can be good in terms of manufacturing costs, will definitely reduce aerodynamic performance. It's better to have, if you can, at each point along the blade to be twisted at the right angle to maximize the energy harvested on average. So they go into off-design conditions and power regulation. So they say early wind turbine generators and gearbox technology require that blades rotate at a fixed rotational velocity, therefore running at non-tip design speed ratios incurred efficiency penalties in all but the rated wind conditions. And I remember learning this like almost 2 decades ago, and I guess, or maybe longer actually, when I was first learning about wind turbines and how they extract energy. And back then, they were like, oh, you can't really run it at off conditions because it's going to be very inefficient, and even the gearbox could be damaged. So it's like just one very narrow range of conditions that the wind turbine can operate at. And it's like, well, what's the point? Now, though, that's not a problem. Their gearbox and generator technology can operate at very different conditions, so very off conditions, and still be quite efficient. They say for larger modern turbines, this is no longer applicable, and it's suggested that the gearbox may be obsolete in future turbines. That'd be pretty cool. Today, the use of fixed-speed turbines is limited to the smaller designs, therefore the associated off-design difficulties are omitted. They also say that the design wind speed is used for optimal dimensioning of the wind turbine blade, which is dependent upon the site wind measurements. So what they do is they go into any site that they're thinking about putting wind turbines in, and they want to measure what the wind is over a given period of time. That way they can determine, okay, this is the average, so we can design our wind turbine to be effective at this average, but it will also fluctuate in these levels. So we want to make sure that when it does fluctuate, we can still get energy. So you want to design the wind turbine not only to meet the best condition, but also non-ideal conditions as well. And again, this is probably being able to come about due to increases in turbine and generator and gearbox technologies of turbines. So they say, as the oncoming wind velocity directly affects the angle of incidence of the resultant airflow onto the blade pitch angle must be altered accordingly. This is known as pitching, which maintains the lift force of the airfoil section. Generally, the full length of the blade is twisted mechanically through the hub to alter the blade angle. So literally, if you have a change in wind velocity, you want to then pitch your entire blade to either increase the angle of attack so you can still generate enough lift to rotate the blades, or reduce the angle of attack to not overload the blades. They say this method is effective at increasing lift in the lower rating conditions, and is also used to prevent overspeed of the rotor, which may lead to generator overload and catastrophic failure of the blades under excess load. Two methods of blade pitching are used to reduce the lift force and therefore the rotational velocity of the rotor during excessive wind speeds. Firstly, decreasing the pitch angle reduces the angle of attack, which therefore reduces the lift generated. This method is known as feathering. The alternative method is to increase the pitch angle, so then you're running the blade at such a high angle attack that it stalls. They say that feathering requires the maximum amount of mechanical movement in the pitching of the blade, but it's still far more favorable because when you have a blade that is pitching, the alternative, when it stalls, then you get not only very high aerodynamic loads in directions that you don't want them to happen, they're often usually very unpredictable. So that means you can greatly damage your wind turbines. So reducing the angle of attack is usually far better. And also they say that if you increase the angle of attack so it stalls, you may also induce fluttering. Now, if you don't know what fluttering is, it's a dynamic phenomenon when any air force, any aerodynamic surface is going under a load, and then it starts to magnify, and then it can just break. That's a very general description. We have podcasts explaining fluttering if you want to watch them later. So they say that full blade feathering pitching at the hub is used by the majority of today's wind turbine market leaders. Feathered pitching offers increased performance, flexibility, and the capability of fully pitching the blades in a part configuration. Manufacturers are reported as using collective pitch in that all the blades are pitched at identical angles. But this is interesting. They say further load reductions can be found by pitching blades individually. Now, I'm not entirely sure why that's possible, but the fact that they're pitching blades individually at different angles of attack, or maybe they're just pitching them when it gets to a certain point in this rotation, I don't know. They say that this is even better and are expected to be widely adopted in the near future. So let's move on to smart blade design. So the current research trend in blade design is so-called smart blades, which alter their shape depending on the wind conditions. With this category of blade design and numerous approaches, which are either aerodynamic control surfaces or smart actuator materials. And this is really cool. The driver behind this research is to limit ultimate loads, so the extremes, and fatigue loads, or to increase dynamic energy capture. They say the use of aerodynamic control surfaces such as aileron-style flaps, camber control, active twist, and boundary layer control are in effect, and we're going to go through those ones individually. So on Figure 6, for those of you playing at home, they have different blades, and ones have active tips, so you can actually change the angle of attack of the tip individually from the rest of the blade. That's really cool. They also have active tip, which means that you can active twist, which means you can actually flex the entire airfoil so you can get different cambers, which is really amazing. And you can get different points at which the camber occurs, and that's really cool. And they have something called active flap, which you have effectively like an aileron on the blade, which is a flap very close to the wingtip, which you can put up or down to change the lift generated and also the drag. Now, one really cool thing they have here is a table comparing all these different aerodynamic concepts in how much more lift you generally generate. And for those of you who know aeronautical engineering, you won't be too surprised by the results here, because the results that you get are very similar to what you would expect in aircraft as well. So, for example, if you have flaps or deformable trailing edges, so in other words, you can pitch the trailing edge down at a great angle of attack, this has a very high effect on the lift coefficient they can produce. And that's the same as for aircraft. So that's not that surprising. And likewise, plasma actuators, let me explain plasma actuators briefly. So plasma actuators are often there to delay stall. That's one of the main mechanisms. And how they do this is by introducing a high momentum flow very close to the surface in the boundary layer. What that does is it re-energizes the boundary layer so that it can continue to flow over the airfoil, the suction surface, when you have an adverse pressure gradient. The adverse pressure gradient acts to reduce the boundary layer velocity, which then results in stall. So by implementing plasma actuators, you then give the boundary layer like a boost of energy, like a boost of velocity, which means they can go further now down the chord without stalling. So that's plasma actuators in a nutshell, and that's a quick crash course for you. And so what they've found here is the benefit that you can get from plasma actuators in terms of the lift coefficient is about 0.1% increase. Sorry, 0.1 increase. So that's again what you'd expect for aircraft as well. Then have microtabs. Microtabs are really cool. They're effectively like they're akin to vortex generators, where they're just this little object that sticks out of the surface, and then that turbulates the flow. And they found that you can increase the lift coefficient by about 0.3. And then also morphing there, that can increase the lift coefficient greatly as well. One difficulty with morphing is the structural side, so the strengthening of it, and so that's something tricky. Active twist, suction blowing, and synthetic jets, they can also increase the lift coefficient quite dramatically by about 0.2. Not as much as flaps, microtabs, or morphing, but still pretty good. Then active vortex generators and plasma actuators, they can increase by about 0.1, so about 1/3 of the maximum that we find with the flaps, microtabs, and morphing. So it's cool having a summation of all these different flow control devices in one handy table. Let's move on to the blade shape summary. So they say an efficient rotor blade consists of several airfoil profiles blended at an angle of twist terminating at a circular flange. So in other words, if you have the blade, when you get to the circular flange, that's how it connects to the hub. And then as you go away from the hub, you get to the wingtip. And they have a nice figure here. Some of it's clear, some of it is not clear at all. I'll go through that in a second. They say it may also include tip geometries for reducing losses to facilitate production. Several simplifications may be made. Reducing the angle of twist, linearization of the chord width, reducing the number of different airfoil profiles. So what that means is reducing the angle of twist means you don't twist it as much. Linearizing the chord width means that you keep the same chord, or you have it increasing at the same rate or decreasing at the same rate along the span, or reducing the number of different airfoil profiles along the span. For a typical blade, they have a figure here, which at the wing root, the blade root, sorry, the airfoil profile is something called an FFA-W3301. And this is a very thick airfoil, and it looks pretty much like a supercritical airfoil if you know what that looks like. It's effectively an airfoil with a very pinched tail, and it's very thick in the midsection. Then as you go along to the wingtip, the chord gets thinner and thinner. Sorry, the thickness gets thinner and thinner. And now at about midspan, they've got something called a DU93W210 airfoil. And this again is very similar to a critical airfoil. It has that very pinched trailing edge, but it's much thinner in the midsection. And also the wing tip, the leading edge, is pinched as well a little bit, so it's not nearly as rounded. So that means that as you go towards the blade tip, the thicknesses of the airfoil sections reduce. Let's move on to blade loads. They say to simplify calculations of the blade loading on wind turbines, because you want to know how much loading is going to be on wind turbines, so you can design it so it meets the requirements and doesn't break. They say it has been suggested that a worst case loading condition be identified for consideration on which all other loads may be tolerated. So again, they just find what the worst case scenario is, design it for that. They say the worst case loading scenario is dependent on the blade size and method of control. For small turbines without blade pitching, a 50-year storm condition would be considered a limiting case. So in other words, they just find out what the worst case was in terms of storms for the last 50 years, and they use that to design their small wind turbines. They say for larger wind turbines, that's not just enough. You need to also consider the loads resulting from the mass of the blade, because they become so great as we'll go through. They say for modern large-scale turbine blades, the analysis of a single governing load case is not sufficient for certification. Therefore, multiple load cases are analyzed. The most important load cases are dependent on individual designs. Typically, priority is given to the following load conditions. So emergency stop scenario, so when you have to just stop the blades on the spot kind of thing, extreme loadings during operation, and parked 50-year storm conditions. So for small turbines, it was only 50-year storm conditions. Now it's 50-year storm conditions, extreme loads during operation, and emergency stops. And then with these scenarios, you have a bunch of different loadings that they need to consider, not only aerodynamic, but gravitational, centrifugal, gyroscopic, and operational, and go through each one of those. As turbines increase in size, the mass of the blade is said to increase proportionally at a cubic rate, and that makes sense. So this goes for pretty much anything in the world, that when you have something that increases in three dimensions, and it keeps its relative aspect ratio. So, for example, let's say a human. If you have a human which is 1 meter tall, and then you put them to 2 meters tall, they don't double in weight. They don't triple or even quadruple. They usually increase by a factor of 8 because they get longer, they get wider, and then they get thicker. So 3 different directions, they get bigger by double. So that's actually to the power of 3, a cubic rate. So the same thing as with blades and everything. So as you increase the blade size, you might double it. Its weight increases by a factor of 8. They say the gravitational and centrifugal forces become critical due to the blade mass, and they elaborate on that. They say gyroscopic loads result from yawing during operation. They are system dependent and generally less intensive than gravitational loads. Operational loads are also system dependent, resulting from pitch, yawing, braking, and generator connection, and can be intensive during emergency stop or grid loss scenarios. Gyroscopic and operational loads can be reduced by adjusting system parameters. Let's talk about the aerodynamic loads first. So the aerodynamic load is generated by lift and drag of the blade airfoil sections. The aerodynamic lift and drag produced are resolved into useful thrust, so that's to rotate the blades around, and reaction forces. And they say it can be seen that the reaction forces are substantially acting in the flatwise bending plane and must be tolerated by the blade with limited deformation. So in other words, the reaction forces are acting to bend the blade, and you don't want that to happen, because not only do you have to then make it structurally strong enough to handle that, you also then have changes in aerodynamic performance, and that's not great. You then have to calculate that, and then it becomes a lot more work. It's just easier to have it much more rigid, and that way you know what the aerodynamic loading is going to be much more easily. The gravitational centrifugal loads. So the gravitational centrifugal forces are mass dependent, and are generally thought to increase cubically with increasing turbine diameter. Therefore, turbines under 10-meter diameters have negligible inertial loads, and they are marginal for 20 meters upwards and critical for 70-meter rotors and above. So the gravitational forces are defined as simply the mass multiplied by the gravitational constant, although its direction remains constantly acting towards the center of the Earth, which causes this alternative cyclic loading case. So in other words, what they're saying here, as the blades go around, because it's being pulled towards the ground of blades, when one blade reaches the peak, the top, the force is at a certain angle. When it rotates around a little bit, it's at a different angle. When it goes down below, it's at again a different angle. So there's a cyclical loading fashion. And so the centrifugal force is a product of rotational velocity squared and mass, and always acts radially outwards. So it, as everyone knows, like if you get a bucket and you rotate it, like you spin it around, the bucket is like pulling you out in the direction that it's flying around in. It's not coming towards you. Now, another interesting loading is flapwise bending. So aerodynamic loads are suggested as a critical design load during a 50-year storm and extreme operating conditions. Once calculated, it is apparent that the load case can be modeled as a cantilever beam with a uniformly distributed load. This is really important because this simplifies the loading calculations. What they're saying is, once you know what the general loading is on the blade, we can then just replicate this as a simple cantilever beam. So it's a beam that is connected at one end and it's free on the other end, and then you just put a uniform load over it. And we have a figure here that shows that kind of thing. If you know static loadings, and then that creates a general bending motion. They say increasing the distance from the central axis of bending gives a cubic increase. What that means is the further out you go, the bending increases not linearly, not quadratically, but cubically. So it just magnifies insanely. They say it is therefore efficient to place load-bearing material in the spar cap region of the blade at extreme positions from the central blade of bending. This signifies why thick airfoil sections are structurally preferred despite their aerodynamic efficiency. So what that means is close to the root, you need to have thick airfoils because they have a very strong bending moments there, and you need to have it strong there so it doesn't break off. Now, fatigue loadings. Fatigue is something that we don't really talk about too much in most things, but is really important because fatigue is responsible for so much more destruction than people think. And fatigue is when you just get whatever, let's say you have a piece of metal and you just bend it back and forth a bunch of times. By the end of it, you can break the metal with far less force, far less stress on the object than if you were to just break it straight away. That's because as you bend something more and more, that's fatigue and it weakens the object. Now, there's a more complicated phenomenon that happens. It gets stiffer because what they call dislocations, which are at the atomic and molecular level, they get intertwined and then it gets stiffer and then it eventually breaks just due to becoming weaker over time. I'm not going to go into that because it's like a whole course in itself, but that's just the general physics behind it. They say fatigue loading can occur when a material is subjected to a repeated non-continuous load, which causes the fatigue limit of the material to be exceeded. It is possible to produce a wind turbine blade capable of operating within the fatigue limit of its materials. However, such a design would require excessive amounts of structural material, resulting in a heavy, large, expensive, and inefficient blade. So fatigue loading conditions are therefore unavoidable in efficient rotor blade design. So let's cover that in English. What they mean is, if you want to design a wind turbine so it can withstand fatigue loading, then it has to be very heavy, and that's not feasible. So what they say is, yeah, we just let it go fatigue and we just figure out how long it would take for it to fatigue, and then we replace it before then. Interestingly, there are some materials out there that you can load as many times as you want, and it will never break. Some materials have a reduction, so if you bend it more and more, they will get to a point where you can even just put in almost no force and it will break. Others will get to a point where it just plateaus out and it doesn't matter whether you load it with a force that is less than that limit, it will never break. And that's, so for example, mild steel, it gets to a point where you can load it 1 million times, 10 million times, 1 billion times, whatever. But if you don't exceed a certain force, it will not break. So that's pretty cool. Moving on to blades here, though, they say fatigue loading is a result of gravitational cyclic loads, which are equal to the number of rotations throughout the lifetime of the turbine, typically 20 years. So what they're saying here is they kind of design the wind turbines to last about 20 years, and I guess after that they reassess it. So I just want to quickly mention here, if you are doing wind tunnel experiments, or any experiments really with air, you need to make sure you're measuring the density of air. The reason why is because it changes from day to day. The temperature, pressure, and humidity all change the density of your air. A lot of aerodynamicists assume that it's just 1.2 or 1.225 kilograms per meter cubed when they're doing their experiments, but it's almost never that. It's usually within about a 2 to 3% range of that, which means that when you do your experiments, you're getting a 2 or 3% error in your results for no reason. Like it's like no good reason. You can get rid of it very easily, which then corrupts all your results a lot. And then that also makes CFD harder to validate because now you have your CFD, which doesn't have the same density as what you actually can measured your experimental results in. So of course they're not going to line up. We make a device called the Atmosphere Hawk that accurately measures the density of air, and it displays it on a very big screen so you can see it anywhere in your wind tunnel. All you need to do is just plug it into the wall. It's that easy to use. Then you just put it on whatever wall you want or a desk, and you can see what the density is in real time. You can factor that in, and you can get very accurate results. Now it gets rid of that 2 or 3% error. So make sure to pick one up. Every aerodynamicist needs one, and you shouldn't leave home without it. Link in the description. So let's move on to structural blade regions. So I mentioned in podcast 51 that unlike airfoils for aircraft, so for planes, for example, they have a slightly different nomenclature for wind turbine blades. So for airfoils, we really just say that the wing tip is just a wing tip. It's like the end tiny little bit. The wing root is pretty much just where it attaches to the fuselage. The rest is pretty much just a span. But here in wind turbines, they have these three general regions, but they classify them a little bit differently. The root goes from where it attaches to the hub, but it goes out a good 20% of the way, and that entire region is called the root. And the reason why they designate this as the root is this is where the aerodynamic efficiencies are lowest, because they make these profiles thicker here to withstand the loadings on the root. So this root region is not really where the aerodynamic efficiency is highest, but it just has to be like that to make sure that the blades don't snap off. Then the midspan and the tip is where you start to get a lot more aerodynamic profiles happening. So that's quite an interesting designation there. That's different to aircraft. So that's the end of this podcast. Make sure to like and subscribe, and check out podcast number 51 for the first part of this series. And also check out our YouTube channel, because we have a lot of different simulations and podcasts on there. And I'll see you in the next podcast. Peace out, amigos.